that we have also received from the Institute. It's a very nice location. And I would also like to take this opportunity to thank actually Kia, Javier, and Yolanda, who did all the work or the hard work in order to make this happen, which is really great. So thank you very much for your work. Yes, and so very important that during the first day, the spirit of this workshop is really to explore physics at the interplay of quantum mechanical systems, interactions, logical order, and driven dissipation or drive anticipation. And so this very well fits also to our first speaker, who is part of our new Forschungsgruppe, which we are all very excited about. It starts very soon. There will be a kickoff meeting sometime in the beginning of the next year. And this is focused around this topic of driven discipline, quantum mechanical systems, or many-body systems. And there are a lot of members here in the audience as well. So you see the logo pop up when posters and talks, I think sometimes, maybe not. In the future. And yeah, so Tobias is part of the Eckert from Berlin, and Christoph Weidberg and Dr. Bo were not here today. But yeah, we are all very excited to work on these topics, and we hope that you see a lot of great results coming out of this collaboration. And so yeah, let's start with the first talk by Tobias on cavity QED systems and driven dissipation.
Thank you very much. And let me also start with, can you hear this? Okay, good. Let me also start with thanking the organizers for the kind invitation and for setting up this beautiful scenery here. And I have really enjoyed so far the talks and the people and the location, of course, also. This is a workshop on collective phenomena. So I wanted to present you some collective phenomena. And the system we are looking at is a Bose-Einstein condensate of atoms, which we put into a high finesse optically resonator. So well, this is moving. Okay. So this arrangement gives rise to long-range interactions, which you can see here on this artistic slide. Two atoms are interacting over long range via the exchange of photons, which are stored inside this resonator. Now, what I would like to show you are interesting many-body states, which are coming out of this arrangement of cavity QED and a Bose-Einstein condensate. And I will show you two different flavors of these. But let me start with explaining these cavity-mediated long-range interactions. What we do is to put a Bose-Einstein condensate of rubidium-87 inside a high-finesse optical cavity. And then we shine light onto these atoms from the side. This is a standing wave laser, which is far detuned from atomic resonance, such that the atoms are not electronically excited, but they just act as scatterers for the light field. At the same time, we put a cavity resonance close by to the frequency of this laser, such that photons scattered off the atoms will preferentially end up inside this resonator. Now, the fundamental process giving rise to these long-range interactions is this following microscopic model. We take a photon from the pump and scatter it at the first atom into the cavity and then back to the pump at the second atom. Now, those two atoms have interacted with each other via the exchange of a photon. And since this photon is delocalized over the entire cavity mode, this is a global range interaction. If you think of what happens to the atoms, then you see that they will acquire recoil momentum kicks. So by scattering a photon, you will acquire one kick here, and the second atom gets its kick in this direction. So at the end, you have now correlated pairs of particles, and they are correlated in their momenta. So we can write down such a type of long-range interaction here. You can also integrate out the light field and then write down an effective interaction potential. And you see that it inherits the modes of the pump and of the cavity. And so in this configuration, it actually favors a checkerboard order of the density modulation of the atoms. We can change the strength of this interaction by either increasing the pump power onto the atoms or by decreasing the detuning between the pump and the cavity resonance. And so all the system is open, so we have photons escaping this cavity. And this is interesting for us on one hand, because this is our observation channel where we can look at real time at quantum trajectories of the system. And on the other hand, we can also study the influence of dissipation onto our system. Now, I told you that the interaction here favors the density modulation, but this does not come for free because the system has to pay kinetic energy, so it has to bend its wave function. So there's an interplay between those two energy scales, and this gives rise to a self-ordering phase transition, which we heard about already in Patamom's talk on Monday. So here is a top view on one of our experiments. You see here actually two cavities which cross on an angle of 60 degrees. What we need for this first part of my talk is only one of those two cavities. And if you think of the lasers, then we have here our incoming transverse pump, which is retro-reflected, and then atoms can sit here at the center and scatter light into the cavity if they self-order in this phase transition. This is a phase diagram. Please. So you see here a phase diagram, and whatever is red colored means that we get photons out of our cavity, so there are photons inside the cavity. And this is shown as a function of the detuning between pump and cavity and the pump strength. So the further you detune, the more you need to pump in order to enter the self-ordered phase. We can not only look at the photons, we can also look directly at the atoms. Here are absorption images after time of flight. No, something happened. What did you do? Oh, okay. Yes, now it works. Good. So these are absorption images after time of flight. And you see in the normal phase, we just get a pure Bose-Einstein condensate, while in the self-ordered phase, we actually get these characteristic momentum peaks, which are there due to the scattering of photons into the cavity. And so these are the Fourier transform of a checkerboard lattice, which the atoms are forming. Okay, this was my primer on self-organization, and now I can tell you what I want to tell you today. I have two topics, possibly three, and the first one is about induced dynamics due to the presence of dissipation in the system, which leads to a pumping of the atoms, and I would like to show you how we then do spectroscopy in the system. And the second part, I would like to come back to these long-range interactions and the creation of correlated pairs of particles, which we can observe. So we are doing a small change to our experiment. We are using now blue detuned light fields. So this transverse pump is blue detuned with respect to the atomic resonance. Atoms are pushed into the dark, but they can still self-order. And the second ingredient is that we have an imbalanced drive. So we send more light from one direction than from the other direction onto the atoms, such that at the end, they experience a standing wave and a running wave component. With these two changes, our phase diagram looks like this. So you see that we now have actually three phases, a normal phase and then two phases carrying photons. And if you can analyze the character of these phases by again taking time of flight images, you see in this upper phase here with this re-entrant phase transition, we have only two more momentum peaks here in addition to the Bose-Einstein condensate. So these are stripes, while this phase here again has this typical checkerboard order. We can get an understanding of why this looks like this if you look at the single particle Hamiltonian, which you see here. Most important are the two lower lines here. They describe the interference between the cavity field and the standing wave and the running wave. So running wave can be written as a cosine and a sine. So you see that we have both components appearing here. One of them is giving rise to the stripes. The other one is giving rise to this checkerboard. Most important is that these two different structures are coupling to the two different quadratures of the cavity field. So A plus Edegger and A minus Edegger, real and imaginary quadrature of the cavity field, which are just distinct by the phase of the light inside the cavity. So using a heterodyne detector, we can actually measure this phase, and then we see that there's actually a pi over 2 phase difference in between those two phases. If we were to look in real space, we would find those stripes and this checkerboard. And if you now ask for the center of mass of this wave function, then you see that it has been shifted in this zone here by, well, lambda over 4. And this corresponds to the full Bragg pattern, which is scattering the photons into the cavity, being shifted by lambda over 4. So this gives you a pi over 2 shift of the light field inside the cavity. That's another explanation. So what I showed you so far is using the dissipation only as an observation channel. But the physics was not really influenced by the dissipation. It was a Hermitian physics which we were looking at. However, we can make dissipation more important. So what we have to do is to enter a regime which we call the dissipative regime, where the energy scale of the photons, which is given by the detuning between pump and cavity, is on the same order as the cavity line width. So this was in the opposite regime, and now we repeat this experiment, going very close to this cavity resonance. You see that we get qualitatively the same type of phase diagrams. However, they look more noisy. This is not noise, this is actually nice data. So if you take one slice along a certain detuning here, then you will find that the time phase of the cavity field is winding from 0 to 7.5 pi in a very monotonous manner. So we still have this, well, n+1 times pi over 2 phase shift between the two, but between the two states of the system, but we have this phase winding in between. So this caught our interest, and we plotted the same data now on a polar plot. As you know it from quantum optics, you have the real and the imaginary quadrature of the cavity field. And then you see that we start here in the real quadrature, the system winds around the phase until it ends up here in the imaginary quadrature. The radial component here tells you that there's always a finite amplitude of this cavity field. And that's important if you think of the atoms which are feeling this interference potential between pump and cavity. So you need to have always some cavity field in order to sustain this lattice which forces the atoms at their positions. So we can rewrite this potential which the atoms feel into a short λ/2 periodic lattice and a long lambda periodic lattice. And this long lattice is sliding with respect to the short lattice as a function of this phase which evolves here in time. So if I play an animation, you see that the potential which the atoms are experiencing is actually moving in space, or it looks like it moves in space. It's periodic, of course. So this is something which reminds us of topological pumping, introduced by Thouless in 1984, which allows for transport of atoms or particles, charges, even in an insulating state. Now, we don't have an insulator, but we still see the same mechanism. There was a nice proposal by Matthias Treuer in 2013 how to implement such a Thouless pump in cold atoms. So he suggested to use a λ/2 periodic lattice and slide a lambda periodic lattice along it. So that's exactly what we do. And this has been also implemented in 2016 in the two groups, one also together with Monika Eidelsberger. And so what they did is to produce these lattices and then use a function generator, I guess, to slide them with respect to each other. And they could show that there was transport. Now, what we do is we don't apply any function generator, but we still have this time evolving phase in our system. And if you think now of this evolution from a stripe to a checkerboard, and each time you have displaced your atoms by λ/4, you understand there's a directionality in the system. So it's a chiral evolution. We implemented an in situ imaging and looked for the center of mass of our wave function, and we could find that it's actually moving in space, directly connected to the number of phase windings which we observe on the cavity. So what we have here is, more generally speaking, an adiabatic pump. And the oldest adiabatic pump is probably one from Archimedes, which had this screw which was dipping into water, and then you are turning a handle. And if you turn this handle in an AC manner, so you return to the same spot every cycle, then you have a DC transport. So what you need is to have a time-dependent Hamiltonian. However, we don't have this time-dependent Hamiltonian. So the question is, who is turning the handle in our case? And the resolution which we found is that it's actually the dissipation. So it's because we have a non-Hermitian system, the system might enter something which is known as a limit cycle, and then it moves on this periodic manner. This is again showing the same data I've shown to you previously, but now I plot, instead of the phase, I'm plotting the frequency. So if you have a running phase, then you know this corresponds to a frequency shift. So here we are at zero frequency, meaning that the light out of the cavity is the same as the light which we send onto the atoms. And then when the system enters this limit cycle, we actually see that it has shifted its frequency to two sidebands. And this is this cyclic evolution which we observed. But what's the origin of this limit cycle? Well, I told you already that it's connected to the dissipation and to non-Hermitian terms. And if you look at literature, then you will find that there's the concept of those exceptional points when you have a system consisting of two modes which are coupled in presence of dissipation. So if you then put your parameters right, you might find an exceptional point at which two of those eigenvalues are meeting, they coalesce, and then you have synchronization in the system, which then can evolve, if there's gain, to have a limit cycle. So there are different realizations of this, always using two modes, for example, in optics or also in optomechanics. And what we now do is, well, to bring this to the world of a many-body system. So how do we make two eigenmodes actually cross in our system? Well, let's start simple and say we only look at the phase transition of which I showed to you at the very beginning. Then we have a ground state and the first excited state. This would be the BEC. This would be the checkerboard border. Now, if you have a control parameter for this phase transition, you will find a mode softening towards a second order phase transition. And at this point here, the system will undergo its phase transition. Now, in the system I've introduced to you, we have more than one mode, or more than two modes, because we have the ground state, the BEC, we have something which we call this stripe mode, and we have this checkerboard mode. And now, changing our control parameter, we can make those excited modes actually cross. And although they are not entering into the ground state, so there's no mode softening to zero, they're still touching each other, and in presence of dissipation, they might coalesce, and this can then give rise to the cyclic evolution. So we set out to investigate whether we can find actually this kind of excitation spectrum, and we started to do spectroscopy on the system. So this again, the phase diagram, and indicated by these two blue and yellow arrows, I tell you what we do in order to find the excitation spectrum when approaching this phase transition. So this is now not about those two modes merging, but it's just the normal phase transitions. We do Bragg spectroscopy, meaning we send a short pulse of light onto the atoms, onto the cavity, and we can tune the frequency of this light with respect to the pump field. And now we look for the response of the system. For example, here we added this pump at 3 kilohertz, and we find a response at plus and minus 3 kilohertz. So this is what happens if we enter here phase 1, which is the stripe phase. Luckily enough, the phase 2, this checkerboard phase, has a different response. So in this case, we only get one sideband. This is because of this running wave and standing wave character. So this allows us to distinguish these two types of excitations, even if they sit on top of each other, which is important for our experiments. So sweeping this frequency, we can look for the height of the response, and then we can nail down where this excitation energy sits. So these are the two mode softenings along the blue and the yellow lines. And now the interesting part is what happens if we do this spectroscopy in the vicinity where those two modes are supposed to cross. So you see that one mode might soften and harden again, and then the second mode comes down, and here's the possibility to cross this mode. So doing our spectroscopy, and this is preliminary data, you see that we find a region in which those two energies seem to be the same. So we indeed find the synchronization. So in our spectra, we find that they sit at almost the same frequency. While if you go further into this phase, or approaching this second self-ordered phase, we find a mode softening of one of them and the other one hardens again. We also found that there's a peak, a sideband imbalance here, which appears, and we connect this to the gain which the system has, and this sends it actually onto this limit cycle. We did a Gross-Pietowski simulation, which you see here, and including also this probing in real time, and there we found, again, this synchronization in this region and then the splitting of the resonance. Okay, so this was part one, what I wanted to talk about, and now we come back to the very beginning. So at the beginning, I told you about these long-range interactions, and that these long-range interactions come from the microscopic process where you scatter a photon from the pump into a cavity and then back into the pump. The question which we asked was, now, are we able to see these correlated pairs of particles in our system? So again, we had to modify our experiment a bit in order to find them or to make it visible. And these are now the modifications. Most importantly, we run our transverse pump, which is now a running wave pump to give the system a directionality. We run it at the tune-out wavelength of rubidium. This means that there's no scalar polarizability. The atoms don't feel any dipole potentials, but they still find the vector polarizability. This means if you have an atom in a certain Zeeman spin state, if it scatters a photon, it has to change its spin. Okay, so we prepare our Bose-Einstein condensate now in the MF equals 1 Zeeman substate of rubidium F equals 1 hyperfine states. And if the atom is now scattering a photon, it has to be scattered into +1 or -1 MF state of the atom. That's the only way it can interact with the light field. We do a very short pulse, only 65 microseconds, and after this pulse, we look what we find in our atoms. That's shown here. It's a combination of a time of flight image and a Stern-Gerlach experiment. So we are able to separate now spatially for our imaging the different spin components, and for each spin component, we know also the momenta. So that's shown here, and I put apart these different pictures such that you can see them. Okay, so what you see is that most of the atoms remain in this MF equals 0 Bose-Einstein condensate. However, some of the atoms have been transferred into MF +1, and they got a positive momentum kick. Other atoms have been transferred into MF equals -1, and they got a negative momentum kick. What I would like to convince you of is that these particles are actually correlated. So these scattered particles, they form pairs which are correlated or can be number squeezed and even possibly entangled. So this is very similar to nonlinear photonics, where you have a nonlinear crystal which you pump with a laser, and out you get a single and an idler photon, which are then correlated with squeezed light. Typically for these kind of systems is a nonlinearity. So if you increase the pumping, there will be a threshold at which the number of pairs actually exponentially shoots up, and that's something which you wanted to observe. So let's look at our microscopic picture of this. As shown here, we take again a single atom, and at the single atom, we scatter a single photon. Now, if we put our cavity resonance on this Raman condition here, then, so because we have shifted the energy of those two states with the magnetic field, then you see that the only thing the system can do is to scatter the photon into the MF equals +1 state. And then this photon will sit inside the cavity until it leaks out of the cavity, and we have popped the atom to the other state. We can suppress this process, this decay process, by detuning our cavity. So now the system wants to get rid of the photon as fast as possible. And this means that it takes the chance and scatters off a second atom into the pump again. So the second atom, due to energy and angular momentum conservation, has to be scattered into the MF equals -1 state. So fulfilling this full process, you see that we have created a pair in MF equals +1 and MF equals -1 atoms. Okay, and if you think of the momenta which are imparted onto the atoms, the first atom is absorbing the photon in Z direction, and the second atom is emitting this photon in Z direction. So this means that also the particles will not only be correlated in their spin states, but also in their momentum states. And that's what we observe. So we believe that these are correlated pairs of particles, and we can now count the number of pairs which we have in our imaging system here, and we see that it indeed behaves non-linearly as a function of the total number of atoms which we put into our Bose-Einstein condensate. So this is this typical characteristic behavior. If you think of these nonlinear processes and think of squeezed light, then you've learned that this squeezed light is induced by a vacuum fluctuation, because you have empty modes at the beginning, and then only this presence of the vacuum fluctuations gives rise to a seeding, which actually puts this photons into this single and idler modes. Now, we want to see if we have a similar situation in our system. So we repeated this experiment as a certain number of particles here many times, and the surprising effect was that if we repeat it under the same conditions, we don't find the same number of pairs. But this number of pairs is highly fluctuating, and it actually follows a statistics which is approximated here by a Bose-Einstein statistics. And that's typically for these processes which are seeded by vacuum fluctuations. So in order to get a better understanding of what goes on here, actually, we set up a truncated Wigner simulation, which takes into account this kind of seeding. And we can first run the simulation with only the vacuum fluctuations as a seed. So there's no population of these excited momentum states. And we find a distribution in our simulation, which is very similar to what we observed in the experiment. Now, since we have this simulation at hand, we can add, well, let's say a single particle into, or single pair of particles into these excited momentum states. And we find that this distribution already looks quite different. And if we just put 5 of those into these excited momentum states, we find that it approaches a Poissonian distribution. So this really distinguishes now the different mechanisms which can lead to this population of these modes. And we believe to be able to say that ours is triggered by these vacuum fluctuations. Finally, I would like to show you the time evolution. We so far applied only this very short pulse. Of course, we can also apply longer pulses. And what we find then is that the population in this different momentum states starts to oscillate. So we have a coherent oscillation of these different momentum populations and spin populations. And this is looking like it's a very useful resource for experiments where we could make use of it at in an interferometer. So you can have interferometric schemes like SU11 interferometers, where you are putting as an input or as a beam splitter, you use an active beam splitter where you have this process, and this allows you to circumpass the shot noise of the system and go towards the Heisenberg scaling. Okay, I think I will not have time to talk about subradiance, which we can also see in our system. But I would like to introduce you to the 2 teams. So these are the people who did the work in the lab, and here are former students which have also contributed. And with this, I would like to thank you for your attention.
Thank you very much for this great presentation. All your time for questions.
So, can you go back to the part where you were describing the mechanism behind the formation of the Wigner cycle? So yes. So in here, so I didn't quite get the argument. So I understand what is synchronization between Wigner cycles, between 3 shades of the Legros. I understand what is an exceptional point. But I didn't quite get how these 2 conspire to form a Wigner cycle. So I understand that if you have an instability of any kind, and if you have the mechanism that can sustain the power after you have instability, then you can have a limit cycle. But I didn't understand how this will explain a limit cycle. How this will value the limit cycle.
Okay, so I would say that the condition which I know of that a system is able to enter a limit cycle is that you need to have 2 eigenmodes which coalesce, if you agree with this. And at this point, you will have actually that in your, if you call this now the real part, that then the imaginary part of your eigenspectrum, you will develop one part which has gain and one part which has loss. And if there's gain in the system, then it is able to enter a limit cycle. The point where they coalesce, I would call the exceptional point, which we don't explore here, but we just pass. And this is the point where, well, you have the zipping of these 2 eigenmodes. And then since there's gain in the system, it's able to start its oscillation. However, in what I've shown you in this experiment here, we see that they zip, so they are at the same frequency, but in this case, we used a cavity which had a smaller line width, which means in this case, it did not start this oscillation. It was just the zipping of the modes. And if we repeat the same experiment in a lossy cavity, we see that then it actually starts cycling. And the precursor of this is what we found, at least, is the side band asymmetry here. So it looks like the system starts like it wants to oscillate, but it didn't really take off.
So in the process where you are showing the pair creation, you show that this exponential scaling. So I guess one can see below the threshold, like there are small distribution effect and then stimulate emission. So when you measure the probability distribution and you show that the process is triggered by particular configuration, you are working here, I suppose, in the relatively small number of atoms in the condensate. And if you would repeat this experiment where you are in the stimulated emission machine, would you see a kind of Quotient distribution there?
No, so let's see if we can read it off here. So the number of pairs is order, so the mean number of pairs here is 1.5 times 10 to the 3. So yes, we are very low. Yes, you're very right. We didn't try, but I agree with you that probably you're changing the distribution and the yes. So I guess the interesting squeezed state only survives the very first events, and as soon as you have passed this point, you have a population, and then you have a self gain if you want, which changes the distribution. So on the list was actually to thermally excite these modes without this process, and then you have an incoherent population already, and ask whether this is seeding it, which might already be the case.
So at the end, you show this time evolution of this equation. And it looked like, yes, this one, yeah. And how I understood the previous thing was that, yeah, they created this pairs. And so they should be equal amounts. But here it looks like
you point to a very hard. Well, it hurts what you say. No, you're right. So you see that this red and the blue points, they should actually do the same thing in sync because they are pairs. But we see that the blues take off and the reds are vanishing. So that's very disappointing. And if I show you what happens at this time here, you see we almost only have blues and not really any red left. So what happens is that this process of scattering a first photon to the cavity and then back to the pump is interrupted because the photon leaves the cavity before it can do the second point. But I told you the solution to this. So we can reduce or we can increase the detuning, and by this make it less likely that this photon is actually populating the cavity. It only virtually populates it. And if you see this, then you see here this imbalance between those two lines, which I've shown to you, as a function of the relative detuning, so relative with respect to the cavity line width. And you see that by going further and further detuned, we can really suppress this process. So we now invested in a big laser, because going further detuned means you need more laser power to drive it. And we now try to suppress this completely and then to use it as an interferometer. Well spotted.
All right. So let's thank Tobias again.